In this video, we're going to be using Coulomb's law to find the net force on a certain charged particle in two different scenarios. One where the charges are all in one dimension, all lined up, and then one where it's in two dimensions and we have some in the vertical and horizontal direction. So for all of these, we're going to definitely be using Coulomb's law. And let's go ahead and start off with this scenario right here. So we're focusing on this 80 microcoulomb charge. And because it has a positive charge next to it, this one is going to be repelling it and then pushing it to the left. So we'll call this one number 1, 2, and 3. So charge 3 is repelling it in that direction. And then the negatively charged particle is going to attract it. So that's actually going to add some additional force in that direction. So we'll say that's from Q1. And then we'll say, for example, if this one was negative and this one was repelling it too, we would just have to take those two and then subtract them from one another. So let's go ahead and use Coulomb's law and find out exactly how much force we have between those charges, and then let's go ahead and sum those up. So now all I did was, since all of these are in microcoulombs, if we scoot the decimal over, so it's just 8.0, then all of them basically turn into times 10 to the negative fifth power instead of the negative sixth for the micro. Now I take everything in my numerator, the constant K, my Q1 and Q2, both my charges involved, and divide it by the separation distance squared. I typically put in the whole numerator, press enter, and then divide it by the 0.2 squared afterwards. So for the charge from Q1, I got 1,260 newtons, which is quite a bit for this little particle here. And then for my Q3, I got 1,620 newtons, a little bit more because this Q value is larger. So that force of repulsion is going to be greater than the force of attraction between these two. Now, as I said, because they're working together, they're both either pushing or pulling to the left. Then you're going to add these two vectors with the tip to tail method and sum them up. And you're basically adding up 1,260 plus 1,620 for a grand total for the net force of 2,880 newtons. Okay, and if you're working on these 1D problems, if the forces are just acting opposite of each other, then you just end up subtracting those two forces to get your net force, but most of the same setup as far as using Coulomb's law to find your forces, except for your final step, you just subtract them instead of adding. Now let's take a look at this two-dimensional case over here. So we're going to use the same numbers as we did previously just to kind of simplify the process of what things we're going to set up. So the separation distance is still 0.2 and then 0.2, and then the charges are still the same, the negative 70, 80, and 90 microcoulomb charge. Just another point that I wanted to mention that I forgot to mention earlier is I just dropped the negative from the charge over here and just took the magnitude of the charge because I already included the direction earlier to the left, knowing that it's a negative charge attracting a positive charge. Okay, so going back to this two-dimensional problem, we know that we have 1,260 newtons from what we called the Q1, and we have 1,620 what we called the Q3, and then we'll call this one the Q2 over here. Now let's go ahead and pull this charge off to the side. Now it's getting attracted by this force over here, so we have a certain amount of force pulling it to the right, and it's getting repelled by this one over here. So we have a certain amount of force pushing it upwards. So let's go ahead and add our force of repulsion first from the 90 microcoulomb charge. So we know that that force is already 1,620. Now it's going to repel it in the upward direction, and we know that's 1,620 newtons. Again, using the tip to tail method, this one is going to get attracted to the negative 70 microcoulomb charge, and that's going to pull it to the right. So then it's going to get pulled this way with 1,260 newtons of force. And what we're going to do is we are going to find the resultant, use the purple vector over here that connects the beginning of the first vector to the end of the second one. And if we just use Pythagorean theorem, we can go ahead and find the magnitude of this force, and that will be our net force. All right, so my final answer came out to 2,052.3 newtons equals C, because it's a squared plus b squared equals c squared. My C, though, is my F net, so that is my final answer for my net force. So in addition to that, I'm going to also find this angle over here so that we have a magnitude and a direction. And what we're going to do is we're going to use the inverse of tangent. You could use the inverse of sine, cosine, or tangent. Just use tangent because I originally had the opposite and adjacent ends anyways. So opposite of that angle is the 1,260, and then my adjacent side is the 1,620. Pop that into my calculator, press enter, and then I get 37.88 degrees as my final direction. So now I have my magnitude and my direction. So for the two-dimensional problems, basically what you're going to do is you're going to combine all of your vertical vectors. Same thing we normally do. If they're in the same direction, you add them up. If in the opposite directions, you subtract them. We're going to combine all of our horizontal vectors the same way, and then we're going to find some kind of magnitude by connecting your first vector to your second vector and then finding the magnitude that way. Now, in this case, we just had one vertical vector and one horizontal vector, so it ended up being fairly simple. Went ahead and used the Pythagorean theorem to get that 2052.3, and then also use the inverse trig function to find the angle. So I hope that was helpful to you, and using Coulomb's law to find the net force in 1D and 2D problems. Thank you for watching and listening.